So we wrote the 2 velocity as dt bar by d tau times a vector with 2 components, 1 and dx bar by dt bar. And this comes from the idea of an invariant. We don't change that invariant property if we multiply this by mass. But we know that if we multiply velocity times the mass, that is a momentum. So let's write PA for the 2 vector that you get when you multiply VA by a constant, the mass. And so that becomes m dt d tau times 1 dx bar by dt bar, which we can write as m dt bar by d tau times 1 v. Now we look at these 2 components, right? So this is a 2 vector with 2 components. The first component, the p0, is m dt bar by d tau, which is m times 1 over 1 minus v squared. Of course, there's actually there's a c in here, but c is equal to 1, right, if you remember. So this is really a v over c, all of that squared. And then there's a p1 component, which is m dt bar by d tau times v. And so introducing the same square root factor, which is called the gamma factor, we get mv over this quantity. So we want to understand what P naught is, what P naught or P0 is. Let's look at, we can make this more familiar by looking at what this term here looks like as the velocity, as v becomes small, it goes to 0. So we want to do, we're thinking of a Taylor expansion, right? So limit as v goes to 0 of 1 over 1 minus v squared, square root. And that is 1 plus v squared over 2 plus higher order terms. There's an even smaller term with a v to the 4th. So we'll just ignore all the other terms. So, but this is enough to get a sense of what this looks like. So we can see that the P naught, now this is an approximation because it's small v, so we get m. Now we're going to replace this with this. So we get 1 plus v squared over 2 plus terms that we can ignore because they're too small. And so this approximates to m plus mv squared over 2. And so we can see from this term here, that's a kinetic energy term, so that this thing must be an energy. And so again, if we throw back in the factor of c, then if we had c not equal to 1, then the P naught in the limit of v being small would approximately be m c squared plus mv squared over 2. we end up getting c divided by c squared here and multiplied by c squared here. So the c's would cancel. But here they would not. You would have a factor of c squared. It looks like that. So like the proper time tau, which is the time on the clock of an observer that's not moving with respect to that clock, we have a zeroth component here, which reduces to this quantity from the perspective of an observer with zero speed. So if this object of mass m isn't moving with respect to some observer, that observer measures an energy which is mc squared. And that's the famous relationship. So everyone agrees on proper time tau and on the proper energy mc squared. So all observers agree on these quantities, that this is the time on a clock that's at rest, and this is the energy of an object that's at rest.